Welcome to the Midlife Men podcast with me, Philip Briscoe. Today, my guest is Samuel Shepherd, physicist, inventor, engineer, holder of 42 patents, and survivor of a terminal cancer diagnosis, and a man who turned a life-threatening disease into one of the most significant breakthroughs in natural anti-inflammatory science. So a very warm welcome to you, Samuel.
Thank you for having me, Philip, and this opportunity.
So let's start by talking about the fact that most people listening will probably know someone who's had a cancer diagnosis, but very few will probably have responded to it in the way that you did. So perhaps you can take us back to early 2000s, what you were told and what went through your mind in those first few days.
Sure. First of all, it wasn't supposed to happen to me. I guess that's a mindset that most people have is, why me? Why did you pick on me? But But with my previous background in the 80s and 90s, being in the petrochemical industry, I worked on electromagnetic pulse weapons, auditory weapons. I may have gotten a little too close to some environmental impacts that had a negative effect on my bone marrow. And had a few electric shocks. I was exposed to some high energy physics, and I got a little careless probably. But in the end, in about 2002, 2001, I started experiencing AFib, blood pressure spikes periodically, and it got progressively worse. And my blood pressure was not controllable by medications. It wasn't uncommon for me to have a blood pressure of, here in the States, of 280 over 160, which was stroke type blood pressures. And I'd go into the emergency room, they would knock me down, and not quite into a coma, but enough to get the pressure down. And thank God every day that I didn't throw a blood clot. I didn't have a stroke. But I went in for a lot of coronary testing. They thought I had maybe heart disease, and it came back all negative. My cardiovascular system was intact, no atherosclerosis, and was overall pretty healthy. But this was sort of unexplained. So after a series of blood tests, I received a phone call on a Sunday night from a nurse, and she said the doctor wanted to see me at 7:30 Monday morning. If you ever get that call, it is never good. And when I went in, the doctor came in and had no nurse, no notebook, nothing. He just sat down and he put his hands on my knees and he said, "Sam," he said, "I've got bad news." And I said, "What's that?" He said, "Well, your blood work came back and you have what's called polycythemia vera." And I said, "Well, what's that?" He said, "It's a bone blood cancer. It's a myeloid proliferative type of cancer." And I said, "Well, what about chemo or radiation?" And he just shook his head no. He said, "There is no protocol or treatment for this." And I looked at him and I said, "What are you telling me?" He said, "This cancer's terminal." He said, "There's no protocols out there." And I just remember looking down at the floor thinking, this can't be real. I had a great life. I financially was in great shape. I had 2 airplanes. I could go anywhere in the world I wanted to go. And all of it became meaningless in the last 30 seconds of this discussion. And it was shocking to me. And I just thought, what was the purpose of life? Why was I here? And I know there was a time involved because he had relaxed and pushed back in his chair. And I said, "Well, how much time do I have?" And he said, in your current condition, you have 10 minutes to 10 years. He said, 97% of the people will perish within 10 years. I said, what about the 10 minutes? And he said, in your current condition, your blood is like ketchup. He said, you could throw a blood clot to your brain, your heart, or your lung right now, and it would take me 10 minutes to declare you dead. He said, we've got to go to the hospital. And that was my first phlebotomy. So they phlebotomized me, and I guess what's the old cliche? The solution to pollution is dilution. So they take the blood out, and they'd put saline back in, and that would keep me going for 30 days. But I could track with my hemoglobin tester the rate at which my bone marrow was producing red blood cells. And it was a standard slope over 30 days. And at the end of 30 days, I'd go in and be phlebotomized again. So it was a sawtooth type of management cycle was the best that we could come up with.
Let me ask you about your mental health as a result of this, because I guess it takes a while for this to sink in. But were you a fighter from the beginning? Did you just think, I am not going to let this beat me despite the diagnosis? Or did you think, well, maybe I just got to manage what's left and make the most of it?
Yeah, it sort of happens in stages, but I felt like I hit a wall. And I only had two choices. I could either go under the wall or I could go over the wall. And then it sort of dawned on me was, of all the projects that I worked on, there's no one on this planet in my mind that had the tools from all of the things I worked in, from kinetics, from biochemistry, from chemical engineering, from physics, from understanding biology. There wasn't many people on the planet in my mind, it's sort of a narcissistic point of view, that had the tools in his toolbox to be able to figure this out. I taught biochemistry for 3 years in Texas. I knew how those cycles and pathways worked. And I could apply engineering techniques, unit operations, mass balance, energy balance. How did these chemical reactions happen? What happened at the protein level? So I had all of these tools in the toolbox, and in my mind, it was nobody on this planet can figure this out better than me. I'm the most motivated, first of all, and I had the will to do it, and I believed that I could figure it out. I had the tools, and now all I had to do was execute. And I come up with this term called WBWD, WBWD, during that period. To be successful in any task, you have to have the will to give up everything you have. No more emotion. Everything was analytical. You got to believe that it's the right thing to do. Drug dealers aren't really all that successful when you think about it. But I believed that this was the right thing to do. You got to have the wherewithal or the tools or know people that have those tools. And all three of those, the will, the belief, and the wherewithal, were absolutely crucial. But they were also simultaneously just not important until you do it. You have to do it. And it was that execution and the motivation to at least run this it's to its final end, do the best I could possibly do. And perseverance was the name of the game.
I guess you had the best motivation going with a terminal diagnosis. And as you said, you believed in your own capabilities. So how did you go about this? Did you have a did you set up a lab? How did you go about starting to look into this?
At that time, I was working on several projects um, with the Department of Defense. I was on the Lunar Outpost Commission in 1991 to 1994, and had a couple projects there that I'd consulted on. So I knew people, and there were a couple projects. One was a way of removing heavy metals from mining industries that came from, at that time, Lieutenant Colonel Tony Wachinski. And then he had asked about the ability, one of the largest pathogen problems, environmental problems in the world was what we were doing with municipal sludges, just by putting them out on the ground and getting people exposed and wildlife exposed. So I came up with a technology that sterilized all of the solids coming out of a wastewater treatment plant. And that went around the world. We put a couple units in England, in the UK. I helped the Chinese in 2003, 2004 to build their wastewater treatment plants for the 2008 Olympics. And then actually in the late 90s, I had consulted with Dr. Clifford Sherry and Dr. Carol Brown at Brooks Air Force Base on the development of electromagnetic pulse weapons, auditory weapons. And each project had its own little nuance to it, different aspects of what I needed to learn to be able to get through those projects. So when this happened, I pulled on every single one of those. I never thought I'd ever use calculus again. Well, it turned out in the development of this, but in excess, I was working on a project in San Diego, and I was well, first of all, one very dark morning, I had gotten up. It was 4:00 in the morning, and had a cup of coffee, and realized that all this was going to end. That was, the part of the mental, and all fear left me. God and I got pretty close at that point, and I questioned a lot of things, and I'd sit there in silence, and it was like the answers in my own logic would come to me and sort of explain what was going on. And I didn't accept inevitability. That wasn't even part of it. And all fear left me. There was no more fear. It was as if I died and was only here temporarily. It's a weird feeling. It was I no longer fear being beheaded. I no longer fear losing my children. I don't ever make decisions that are prefaced with the word, well, I'm going to do this because I'm afraid if I don't. That never entered into any of the decision making that I had. So it sort of came to me that and I had access to a government database as a result of the projects called ProQuest. But it came to me, there's got to be something here that God created, because he created this perfectly. That came to me. And therefore, cancer is an aberration. It shouldn't be here. So there's got to be some creatures that apparently don't get cancer. Something, a leaf, a vegetable, an animal, something. So I queried the database and asked for all animals that don't get cancer, or there's been no recorded cases of cancer. Well, the query came back that there were 5. Since then, we now know of 2 others, but it was salmon, pink flamingos, sharks, elephants, and naked mole rats. And there apparently is no known cases of cancer in any of those animals in all the research that's been done for the last 100 years.
Is there any pattern there? Are there anything they share in their genetic makeup or anything like that?
You came to the same conclusion I came to. So they're all different species biologically. There shouldn't be any link between any of those. And this is all sitting down in this meditative, don't bother me state that allowed me to think through this. So, Scripps Oceanographic had a lot of data on animals, and I was sitting in a hotel bar. We were working on a project together, and I asked him, I said, can you get tissue samples from these 5 animals? And I want you to run a screening algorithm, a test, a mass spec on them. And I said, I want to know every single molecule that's in all 5 of these species, but I want you to put in a screening algorithm so that I want to screen out lipids, proteins, carbohydrates, enzymes that should be found in those animals. And I want to look for the molecules that is found in all 5, but should not be in any of them. And he agreed. And so Scripps, I got a phone call about 4 months later, and they said they found one. And I was shocked, first of all, that there was one, and then that there was only one. Why did it lock into one? That was another thing that I probably dwelt on much longer than I should have. But it turned out to be astaxanthin was found in all 5 of those animals, and it shouldn't be in any of them. It's not made by the animal. It's not necessary for their existence, and yet it was found in all 5.
And what is that for those of us that don't know?
Yeah, astaxanthin is a carotenoid that's produced by an algae called Haematococcus pluvialis, and it grows in very hostile environments, saline water, the Salton Sea, for example, the Dead Sea in Israel, in desert environments, savannas. And what happens is this algae, which is a green algae that exists during its life cycle as a green algae. Then what happens is when its pond begins to dry up, it knows it's going to perish from the intense UV radiation of the sun, we believe, because as the pond begins to dry up, it immediately starts producing this powerful carotenoid called astaxanthin, and it pushes it out to its cell membrane, almost like a tanning molecule to absorb the UV radiation that would normally kill the algae. Now it's being neutralized by this molecule on its cell membrane. So the pond dries up, the algae sinks into the mud, and it lives for 100 years waiting for the next rainfall. And it forms a cyst, and then when the rainfall comes back, it recysts, it forms back into a green algae, and it continues its life cycle. So that's what we've learned since then, how this works.
So how was that in those 5 species then, those 5 different animals?
That's another great question, Philip. I asked the same question. How did this astaxanthin get into an elephant? How did it get into a pink flamingo? How did it get into the salmon? Well, this algae grows even in the ocean, in the salt environments. So the protozoa eat the algae, the shrimp eat the protozoa, and it goes up the food chain. And since it's lipid soluble, it bioaccumulates. Same as fish oil. Fish oil doesn't come from fish. All fish oil comes from algae, and it bioaccumulates in the fish because of their diet. Well, the astaxanthin does the same thing. So salmon eat the herring out in the ocean, and they bioaccumulate this powerful carotenoid, and it's what turns salmon pink. That's why we have the salmon color. But more importantly, we found that that's how salmon go through the extremely stressful life cycle of moving from ocean to fresh water to lay their eggs. It's extremely stressful. And most fish die from oxidative stress during that cycle, but salmon and some other fish have adapted this carotenoid to protect them from these oxidative stress molecules that they generate in this. And astaxanthin was the key. So that's why salmon are pink. Pink flamingos get it when they sift through the salty saline water where this algae grows, and they suck it up. And that's what causes the feathers to be pink in pink flamingos. Elephants, which was the one that really intrigued me, was on the savannah, water is precious. So they try to find whatever water holes they can. Usually the water holes are heavily polluted from other animal manures, lions, hippos. It's high in nutrients. Well, that high nutrient level causes an extreme propagation of this algae. It feeds the algae there, and the salty, as the water evaporates, the conditions are perfect for this Haematococcus pluvialis to grow. So when the elephant comes in for a drink, his trunk is like a fire hose. He just sucks up water, sucks up all this algae, and anything that's in the water, any of the debris. We're not talking fresh water here that he's pulling up through his trunk. So he accumulates huge amounts of this algal biomass into his stomach, and he rapidly absorbs that. That's why elephant tissue is pink. Their ears are pink. When they talk about pink elephants, but their skin has that pigment in it. The mole rat is a little different. It's the ugliest creature I've ever seen in my life, but it lives underground, and it only eats a yeast off of the roots of grasses. When it eats the roots, it picks this up, but that yeast also produces astaxanthin. And we think that's how the mole rat, which is pink in color also, gets the high concentration of astaxanthin. Sharks get it from bioaccumulation of salmon that they eat, other fish that they eat. So they bioaccumulate probably through the herring or through fish schools, but they all end up with it. But since then, we know that shrimp and lobsters don't get cancer. And you see it when you boil up shrimp, they turn red. You see that red color come out in their tissue. That's the astaxanthin that's coming out during that oxidative stress condition called cooking.
So were you the first person to discover this?
I don't know. There wasn't a lot of literature, but it was in that database. So universities like the University of Arizona, which I researched heavily, they led to it. Scripps Oceanographic did a lot of work on it. I worked, once I found this out, then I went to the University of Texas that carries an algae library, 3,300 different species they keep alive. So I got a sample of the Haematococcus pluvialis, brought it home, and got one of those, I call them hillbilly hot tubs, but they're the Intex blow-up hot tubs that you can put in your backyard. And the reason I did it, it had a heater. I could control temperature. I could control air bubbling when I injected CO2 to keep the algae alive. And then I could cover it with a piece of clear plastic for photosynthesis and bungee cord it, and it blew itself up. It looked like a dome-shaped greenhouse, an aquatic tank. And I got very good at growing this algae. And then the DARPA, under the Department of Defense, was working on a project to develop high-altitude jet fuel called JP-8. And what we found was the fatty acids produced by these algal species allowed the jet fuel to have a gel point instead of minus 42 degrees centigrade. We could make a jet fuel that was minus 56 centigrade. So that allowed the jet to operate at, and you can calculate what altitude these spy planes are now designed to run at, without the fuel forming a gel or a solid in their fuel tanks. So since I was, at that point, was an expert at growing and maximizing reactor design to maximize algal growth, which several of the patents are based on. I got brought into that program.
So all the time you are living with this diagnosis, and as you said, you have this kind of mindset, very focused mindset, that you're going to do something about this, and you've got all the tools to do it. So were you thinking the whole time, how do I take these discoveries, especially this astaxanthin, molecule? How am I what am I going to do with that could then help me in terms of my diagnosis and my way forward?
It come back to textbook, because that's what I referred to, because this was so novel. There wasn't any clinical work that I could fall back on from a biomedical point of view. So my background was in very structured textbook biochemistry. And I had worked in the polymer industry where we used free radicals to initiate polymerization in polyethylene, polystyrene, polyvinyl chloride, and these mass polymerizations. So I was an expert at free radical chemistry. And when I began to look at the ability of these free radicals to steal an electron from organic compounds, it was almost like a light bulb went off, because that's what was causing protein misfolding, for example, in type 2 diabetes. I also knew on the DNA level and the genetic level that the guanine, the G part of the code, G and C, T and A, the G part, the guanine, has the lowest oxidation potential, which means it has the highest propensity to donate an electron to these free radicals. So if your concentration of free radicals go up, statistically, the probability is it's going to mutate or steal that electron from the guanine portion of the DNA. That was important, because if the guanine gets mutated, and we have 3 DNA repair mechanisms. We have PARP, BRCA1, BRCA2. If it tries to repair that and it finds that it's misfolded, the PARP, the repair enzyme, will convert the G to a T. The complementary of the G is the C. So now the C will not attach to the T. So the BRCA goes over and changes the C to an A. Now you've just mutated your DNA. That affects the P53 enzymatic, and it's probably the prelude, although we don't know definitively yet. That's what causes cancer.
So if you can mutate your DNA, as you've just described, you can potentially then stop or prevent cancers occurring in your body.
The only way I know to stop cancer is to kill it. I'm not a geneticist. I didn't approach it from a genetic modification, although I know that's going on. But at that time, I was only interested in finding a way to kill it. So once the cancer begins to form, and cancer will start 5 to 15 years before it ever presents, depending on the type of cancer. So that's what makes it so difficult. It's a chronic progression, not an acute. You don't wake up one day, get cancer one day, and you end up with a big tumor the next day. It can take up to 15 years before the cancer will actually present. So now the cancers I was dealing with, including my own, was already in a state of progression. So I had to stop it at that level. So when you go to an oncologist, let's see, the best analogy is a giant oak tree. You got the root structure, you got the trunk, you got all the branches coming off. Well, doctors stand on the ground and they just treat the branches. You got type 2 diabetes, you got cancer, you got Alzheimer's, Parkinson's, whatever, heart disease. And they just treat the symptoms, the branches. We could go down to the cause in the root structure and look at diet, UV exposure, but these are hard things to control. Very difficult to manage over long periods of time, because you're going to slip up. You're going to do something. You're going to get exposed to something. But where it narrows down is the trunk of the tree. And that trunk of the tree is comprised of only 4 major free radicals: singlet oxygen, superoxide, the peroxyl, or the hydroxyl free radical. That was where I focused. That was the choke point. If I could stop those 4 free radicals from progressing up the trunk of the tree and presenting as disease, I could choke off the disease. And that's what I focused on.
And how did you end up doing that then? How did you end up stopping it?
From the textbook, and all doctors are taught biochemistry. It's all in those books. Those 4 free radicals are not only communicators between cells, excess of those free radicals cause disease. So when we're young, we have a concentration of these reactive oxygen species, but we don't get diseases. We don't get cancer when we're 20, 25. You don't hear of a lot of cancers in young people. So when we looked at the biological pathways, we find that the mitochondria that generates these free radicals, by the way, from sugar conversion through the citric cycle and the Krebs cycle, it generates these free radicals. But when we're young, we have 3 cellular antioxidants that protect us: glutathione, catalase, and superoxide dismutase. And when we're young, we're producing large amounts of these intracellular, inside the cell. But at the average age of 42 in women and age 50 in men, nature cuts off our ability to produce these cellular antioxidants. Our life habits have never changed. We don't change how much alcohol we drink, how many cigarettes we smoke, how much fruit we eat. We don't change those things. But now the protector, the shield, has gone away. And we get what's called these age-onset diseases. We start usually with arthritis. It'll start in the joints. You'll get some stiffness in the morning. You think, oh, that's just because I'm getting old. No, it's because you're no longer efficiently producing those cellular antioxidants. So what the astaxanthin does, and I'll explain what separates the Volasta from the astaxanthin, but what the astaxanthin does, it's the most powerful natural antioxidant on planet Earth. And it will donate an electron to those free radicals and neutralize those, convert those back into water, or allow them to be converted into water. And we can get rid of those. So when we found that out, we found that now you could take an oral natural material and it would get into the cellular structure because of its makeup. It is fat soluble. It is a molecule that can live in the phospholipid membrane of every cell and protect these transient electrons, these transient free radicals, from getting into the nuclear envelope and causing these mutations. So with cancer cells, we also found that the astaxanthin, Dr. Allison at MD Anderson won the Nobel Peace Prize on this, and it really answered a lot of the questions as to why this was working so effectively. We started giving it to family and friends in 2013, and their cancers began to go away. And I didn't have a full explanation as to why. I'm not a big anecdotal guy. If someone tells me, you need to eat the bark off of this tree, and it cured me of cancer. And when I ask them, how did it cure you of cancer? And they don't know. They say, I don't know, but it cured. I run away from those as fast as I can. I have to know why did this work before I could commit to it. So when I began to see these rapid results of these cancers being stopped, and the oncologists were now questioning it because they had never seen anything. They called it miraculous remissions. But the common element was everybody who was getting these remissions were taking Volasta. So that sort of rang a bell, and I can go through some comments that we had from that too.
And you were taking it yourself, I guess.
I Yeah, and I still take it. I'm not going back to where I was. Um, but but one thing that the way I started taking it, going back to the first reactor, was I would grow the algae. I'd uh, turn it red by adding salt. I made it think that its pond was drying up. So I would just add salt, increase the salinity level, and the algae within 24, 36 hours would turn red. And I would float it to the top, skim it off, put it in a dehydrator, and I would dry it to less than 10% moisture. And then I used that powder and I would put it on my food. I'd put it in my cereal, on my salads. And I knew it was 3.8% astaxanthin. And so I could set a dose, let's say 5 milligrams, and I could calculate how many grams of this biomass do I have to eat to give me a 5 gram per day dose. So I started out at 5 milligrams per day. And instead of my phlebotomies being once a month, the slope of the curve went down to about once every 2 months. Statistically, it wasn't significant. It was still within the noise level of the control, but it wasn't killing me either. Red things like red berries are oftentimes toxic. You don't want to just do that. And I didn't know what it was going to do to my kidney or my liver. So I was very careful. I did it at 5 milligrams, began to do blood work. My blood work was unaffected. And my phlebotomies were now every 2 months instead of every month. So I thought, okay, this is pretty good. So I tripled the dose. I went to 12 to 15 milligrams per day. And my phlebotomies got pushed out to once every 4 months. Only 3 times a year was I now being phlebotomized. That was significant. And so now I had 3 slopes of the curve. I had the control, no astaxanthin. I had 5 milligrams, 5 milligrams per day, and then 12 milligrams per day. So now mathematically, and I used a pretty typical equation, which is the inverse of the square root for dosing. That was pharmacies use that to determine dosing from animal to humans. So I used that same equation and I said, okay, how much do I have to take so that I'm never phlebotomized for the next 50 years of my life? And it turned out to be 96 milligrams. And I started taking 100, and Philip, my phlebotomies ended. But I'm now eating a lot of algae. And so I thought I'd be clever as an engineer, and I would just extract the astaxanthin from the biomass using a unit operation called supercritical CO2 extraction. And I was successful, got very, very pure astaxanthin from that. So I started taking it at 100 milligrams of the pure astaxanthin, and my cancer returned. My hemoglobin began to climb out again. And I just kept increasing the dose, trying to figure out, how do I turn this? How do I get this to stop? And I was well over 800 milligrams a day before it finally turned over in my hemoglobin. At that point, I was then getting phlebotomized again. But it did roll over at about 800 milligrams a day, which is a pretty high dose. And so I thought, what was the difference? Because if I was eating the biomass, I'm equivalent of 100 milligrams per day. But if I eat the pure astaxanthin, which was counterintuitive, I'm well over 800 milligrams. So when I went back in and look at the mass spec of the astaxanthin as it exists in the biomass, it's in 2 forms. It has a fatty acid attached to the astaxanthin, or it has a glucose molecule attached to the astaxanthin. But in the process, I cracked that fatty acid and that glucose off of the molecule because it's 2,200 pounds of pressure. And the glucose, the ether bond holding it on there would crack and come off. So you end up with a pure astaxanthin. So I thought, it's the glucose. That was the key for the absorption. or the lipid, one or the other. That was the only difference that I found between those two states, those two products. So I go back to the electromagnetic pulse chemistry, the electrochemistry portion of adding things to organic compounds. And so I took the glucose and exposed it to a high frequency, and that is now patented. That is a U.S. patent that shows exactly how that was done. So I reattached the sugar to the astaxanthin. So now when you eat this, it goes into your small bowel. That glucose is highly favored, readily absorbed. Well, it's chemically attached. It's called a Trojan horse, and we use this in bioweapons development. And it would pull it into the bloodstream. Now this glucosidic astaxanthin is floating around in your bloodstream. Well, when it gets close to a cancer cell, guess what cancer really likes? It loves sugar. And it uses 16 times more sugar to generate the same energy as a normal cell does. So when it sees that sugar, it pulls it in with it. Well, it's a Trojan horse. The sugar goes in, pulls the astaxanthin intracellular. The enzymes crack that sugar off, and it feeds the cancer. Now the astaxanthin is intracellular. It's inside the cell. Well, cancer cells, when it processes sugar has a lot of OHs, oxygen, hydrogen, hydroxyl groups hanging off of it. And when it processes that, hopefully, those OHs are converted into H2O, water. But in cases like cancer, the metabolic rate is so high and so inefficient, you get the OHs becoming free radicals. There's an electron leakage. And the electron in the outermost orbital isn't there. And that makes the hydroxyl free radical extremely reactive. Well, the cancer has to push that out, and it pushes it to the extracellular through the membrane outside the cell. So the cancer, the hydroxyl free radical carries an acid pH, slightly acidic, less than 7 on the pH scale. So this is all residing outside the cancer cell, and it kills adjacent normal cells and makes room for the cancer to grow. It's pretty hideous the way that the cancer works. Well, now you have all these hydroxyl free radicals sitting out there looking for an electron, and whatever they touch, they pretty much destroy the existence or the structure of that protein. So when the astaxanthin comes in, astaxanthin can donate an electron without itself becoming a free radical. It has a resonant capability down its long organic chain. Well, when it donates an electron to an OH having a 0 charge, and all that means is that it has in its outermost orbital, it's missing an electron. When it donates an electron to that, it becomes an OH -1. Electrons carry a -1 charge. That becomes a hydroxyl ion. That shoots the pH well over 9, and under the Warburg alkalinity studies that he had done, that OH -1 reacts with the fatty acids in the cell membrane of the cancer, causes those fatty acids to become water soluble. If that membrane becomes water soluble, the membrane splits. All the guts of the cancer cell flood out into the extracellular cytoplasm, and the cancer cell dies. So there's two mechanisms of kill. One is the astaxanthin sticks to the end of the PD-L1. Now, what the PD-L1 is a protein that sticks out through the cell that our T cell, this PD-L1 exists on all cells, normal cells and cancer cells, but they're highly prolific on cancer cells. But when our T cells come down to sniff all these cells, it has a PD-1. If the PD-1 makes contact with the PD-L1, your immune system runs away. It won't kill it. Bacteria doesn't have PD-L1s. Viruses don't have PD-L1s. Fungi don't have it. So your immune system will try to kill it. Cancer has it. And that's the defense mechanism that Dr. Allison won the Nobel Peace Prize on. Astaxanthin reacts and sticks to the end of the PD-L1. Now I have this molecule stuck to the end of the PD-L1, so when the T cell comes down, it can't make contact with it. It's inhibited. This is the basis of immunotherapy, by the way. If it cannot make contact, it will kill that cell in 4 seconds. It's violent to watch under a microscope.
So this is an amazing discovery then, in terms of So why is it not more prolific? Why are people still, suffering from cancers, dying from cancers? Why? Because this sounds like this is the cure-all. This could wipe it out.
We're not quite there yet, but we're in 27 countries. We're in all 50 states of the United States, and the medical industry is only recently beginning to promote it. They thought it was snake oil. In April of 2019, I testified in Washington, and there were about 200 senators, representatives, lay people, 5 major hospitals, Johns Hopkins, Sloan Kettering, MD Anderson, Mayo, and the Cleveland Clinic were all in attendance. Went on for 2 hours, and they were shocked because it completely disrupts the current idea as to how to treat cancer through brute force with chemo and radiation. This is truly an understanding as to why cancer works from a biochemical point of view, and allows a very systemic and analytical way of going in and attacking it without the side effects. There's no side effects to this. Arthritis goes away in 7 to 10 days. All 3, rheumatoid, osteo, and psoriatic. Hashimoto's disease, which is inflammation of the thyroid, goes away. The inflammation caused by Lyme disease or Crohn's or diverticulitis, within 2 weeks, they see results. This is a game changer, and it approaches medicine from a whole different angle. Now, to answer your question, if you were a doctor trained in one field and you knew nothing about this, which one would you promote?
Yeah, I guess the one that everyone uses or has done until now.
Well, there's money in it.
I guess this is I guess you're taking, I guess, in powder form, as you said. So you're taking tablets, and that high dosage, if you continue to take that, is having the effect with 0 side effects. And I guess, is it applicable to any sort of inflammation, cancers, and other sorts of disease that are generating, inflammation around, joints and cells?
The National Institute of Health, after I spoke in April of 2019, you can look up. They allocated funds, I think, to prove me wrong, which is okay from a scientific point of view. But they allocated funds to further the research. So you can Google or search NIH and astaxanthin and cancer, and you'll see all of the research that's been done confirming my findings, independent of me. I didn't participate in any of the ancillary research that was done, but they've now confirmed that this, in fact, is real. That was not often in my life of things that I developed did what we calculated on a piece of paper actually existed in physical reality. There was always some nuance or change that we had to apply to get it to. This was textbook. And that's why they got so concerned, was there was no clinical work needed. If we'd had just gone back to our basic understanding of biochemistry from a textbook or from a free radical chemistry course, a lot of the books in the background are courses that I had taken in free radical chemistry. And it all made perfect sense when I could pull from all those different disciplines to this point in my life. It all came together. It worked beautifully. It held to be sound. And then these independent research papers have confirmed it.
So what would your advice be to someone listening to this who is suffering from, some sort of illness, whether it's cancer or whether it's some of the other illnesses that you talked about, what would you suggest they might do? Because they're going to be very interested hearing about this. Would you suggest that they go and research this and have a look into it and look at the finding?
Always do the research. I'm only a talking head. That's just a messenger bringing this, and I don't expect people, to really just believe me and what I'm saying. Do the research, but first of all, prevention is the name of the game. We now have a blood test called an HSCRP. And you can ask your doctor to run that. He'll give you every reason why he does not want to run it. He'll tell you your insurance doesn't pay for it. It's not something that they follow because they can't treat to it. But if that HSCRP is over 3 milligrams per liter or equivalent, it's only a matter of time before you're going to present with some sort of an inflammatory disease. It can be as simple as arthritis, maybe some irritable bowel issues, or it could eventually result in Alzheimer's and Parkinson's and MS. That's how severe that test is. Everyone should be running it. If that, we want to drive the HSCRP less than 3 milligrams per liter. Once it's below 3 milligrams per liter, you have less than a 2% chance during your lifetime of getting one of these diseases. That's the key.
Because we hear that, often statistics like, 1 in 2 people will get cancer in their life. I mean, this completely
shatters it.
That. Yeah. If people want to research this for themselves, where should they go? Where should they look?
I would go first to the National Institute of Health and look at some of the independent research that's been done since 2019. You could Google or search NIH and 2019 and astaxanthin and whatever disease, cancer, heart disease, arthritis.
So Valasta is the the output that you've produced then?
Correct. Valasta is the astaxanthin that has the glucose molecule. It's the glucosidic form of astaxanthin. It's the only known form that at that dose level actually works. And we just increase the absorption rate by adding that sugar molecule on it. We allow it to move to every single cell in your body. And that was the game changer. And that's why the U.S. Patent Office allowed this supplement to be patented. It's the only supplement that has ever been allowed to be patented. And the FDA got concerned because the title of the patent is a method for the process of using astaxanthin for the treatment of inflammatory disease, particularly for the treatment of cancer. Nobody likes in the regulatory world words like treatment, cure, diagnose. Those are bad words that we're not allowed to use, but that they allowed this because of the overwhelming evidence.
So how do you buy Valasta? Is it available in health food shops and online stores? Where do you find it?
Yeah, it's typically over the internet. We ship around the world. We have marketing distribution centers in Denmark, Australia, Singapore, in the UK. But just go to valasta.net. And it's VALASTA. And it comes from valuable astaxanthin. And you can order it there. It's in a chocolate form. It's in an oil form. It's in a capsule form. And it ships directly to your doorstep without a prescription.
Right. Well, we'll put those links in the notes as well. I think we're out of time, Samuel, but I just wanted to thank you again for your insights. Really fascinating. We'll put those links in. We'll put the links to the NIH in there as well, as people can have a look at for themselves. But yes, just remains for me to say thank you. Thank you for joining us.
Thank you, Philip, for having me on and getting word out to people that there still is hope.
Thank you for listening to the Midlife Men podcast with me, Philip Briscoe. If you want to find independent research on astaxanthin, go to the National Institute of Health website or the National Centre for Biotechnology Information at the National Library for Medicine. To find out more about Valasta as a supplement, then visit valasta.net. To help raise the profile of this podcast, it really helps if you can please review, rate, follow the show on your favourite podcast platform, and please share it with your networks and people you think might benefit from listening. If you have a story to share, then do please contact me through the website mid-lifemen.com.